So last time I stated this lifting theorem. That was somehow the key point of the proof. And today I want to finish the proof of this lifting theorem. Let me recall the statement. So what was called n yesterday is now called g. So it's fixed integer. And so we had the Siegel moduli space, Ag gamma, say, so being the quotient of this Siegel upper half space by some congruent subgroup gamma. Some level gamma. And so the lifting theorem says the following. That any Hacker eigenvalue system appearing in some, well, let me slightly switch setup. So last time I was considering some homology group. This time I'm considering compactly supported cohomology. You can easily see that the two statements are equivalent. Any Hacker eigenvalue system which appears in some compactly supported cohomology group lifts to a Hacker eigenvalue system. Of some classical cusp form. Okay, and so as I said yesterday, the proof uses the p-adic geometry of these spaces. And so let me give a slightly more precise version of the theorem I stated yesterday. So let me work with a minimal compactification. Which is also sometimes called the Satake or Bailey-Borel compactification. So Satake constructed this as a topological space, and then Bailey-Borel showed that this has a canonical algebraic structure. Ag gamma star. And again, I'm passing up a p-adic tower. So I let gamma p to the m be the subgroup of those elements which are congruent to 1 mod p to the n. So this gamma here was some subgroup of the symplectic group. Okay. The theorem said that, the first part said that it doesn't make sense to go to the infinite level as some kind of rigid analytic, in some p-adic analytic world. So there exists a perfectoid space, Ag gamma p infinity star over my p-adic field Cp such that this is, in some sense, the inverse limit of all n of these guys. When you consider them, first of all, you base change them to this p-adic field. So a priori, they started life as some kind of real or complex manifolds, and they became algebraic varieties, and now you consider them over the p-adic field. And there you consider them as some kind of p-adic spaces. And so it doesn't make sense to go to infinite level here. And then at infinite level, there exists this Hodge-Tate period map. which goes from this infinite level guy and goes to some flag variety. Where this flag variety here parameterizes totally isotropic subspaces of, say, Cp to the 2g. Equipped with that standard symplectic form which we use in all this business. And so this has a couple of good properties. So it's equivariant. So because we took this inverse limit here, the p-adic group really now really acts as a group. We don't just have Hecke correspondences, but a real group action here. And so it also acts on this flag variety. So this, because this lives over some p-adic field now. So that's sp2g qp equivariant. It's also equivariant for the Hecke operators away from P. Hecke operators prime to P. With respect to the trivial action on the flag variety. Moreover, and this is important for the application, this map is affinoid, meaning that there is a cover of this guy by open affinoid subsets whose preimages are affinoid subsets of this infinite level guy. So this map has some very strange properties. So for example, it satisfies the evaluative criterion of properness, and it's kind of affine, but it's very far from being finite. This should be sort of as some kind of analog of Borel embedding, yeah. So this SG, this Siegel upper half space, lives in the complex world and is naturally a subset of this flag variety, the Borel embedding. And yeah, this is some kind of p-adic analog of that. And let me first write this and then explain. So all, at least semi-simple, automorphic vector bundles come via pullback. From the flag variety. So why is this a reason? So that's a script F and then an L, right? Not an H or something. So why is this a reasonable statement to believe? So how are these automorphic vector bundles defined? So in the complex world, you take this Borel embedding, you have these vector bundles here, which come from representations of the parabolic subgroup. And then you pull them back, and then they become G-equivariant vector bundles here, well, somehow on this SG, but then by equivariance they descend down. And some of the same picture is true here. Okay. I mean, I could just take QP here, that's okay. Yeah. Yes, I mean, I might just, but I mean, for the applications, I really want to work over an algebraically closed field, so I'll just do this from the start. But yeah, you could make sense of everything. And in my paper, I do make sense of everything just by tendering with QP.
One can put many fields there, QP, CP, and other fields.
Well, any p-adic field, yeah.
Sorry?
Any p-adic field. But I mean, it really doesn't really make a difference, right? So it's just like, I mean, if you do it for QP, then you get some space, and then all the other spaces are just scalar extensions of this guy. So, yeah. Okay, so so yesterday I was just talking about this for the case g equals 1, and now I want to explain the geometry in that case. So let me use the notation m gamma p infinity star. I mean, as in my last talk somehow, for the modular curve. So you have the Hot-state period map, which goes to P1. And so this is some periodic analytic space, and so mod P, the modular curve, has a natural stratification into the ordinary locus and the supersingular locus, and this induces a similar stratification of all these modular curves at finite level, considered as a periodic space, and then also at infinite level. So that's naturally decomposed into an ordinary part and a supersingular part. And so actually this decomposition comes via pullback from a decomposition of P1. And what's this decomposition of P1? It's a decomposition into the rational points of P1 and what's called Greenfeld's upper half space. So it's a complement of the rational points. Greenfeld's upper half space. This commutes. So in particular, connected components of this guy get contracted to points. So there's very little geometry going on the ordinary locus, whereas there's something very interesting going on the supersingular part. And in particular, this map has some of these very strange properties that if you start somewhere in the ordinary locus and then slowly walk into the supersingular locus, then the image under this map will stay constant for a time, and then suddenly only will start to move. Well, something similar could certainly not happen for some usual finite type spaces, but in this highly non-Euclidean situation, it is possible. Okay, so let me describe the map on the two strata. So on the ordinary locus, what this map does is that it simply measures the position of the canonical subgroup. And so the canonical subgroup is for an ordinary elliptic curve that's some uncharacteristic P. It's just this, you have the canonical decomposition into a multiplicative and an étale part. And so in particular, the multiplicative part in the p-divisible group gives you a canonical one-dimensional sub, which induces a canonical one-dimensional sub also of the p-adic Tate module and characteristic 0 then. And if you trivialize the whole Tate module, then it gives you some a canonical line inside of ZP squared. So an element of P1 of ZP or equivalently P1 of QP. So on the other hand, if you look at the supersingular locus, then, so what is the supersingular locus? So at level 0, in characteristic P, you have finitely many supersingular points, and each of them gives you an open unit disk in the generic fiber. And then as you pass up the p-power tower, you will always get these Lubin-Tate coverings of all these open unit disks. So what you will get is a finite disjoint union of Lubin-Tate spaces at infinite level. So in LT infinity, that's some Lubin-Tate space. Infinite level. But then there's a theorem of Faltings. Refined first by Farg and then in my joint work with Gerard Weinstein, which says that this is isomorphic. This Lubin-Tate tower at infinite level is isomorphic to what's called the Drinfeld tower at infinite level. Drinfeld space at infinite level. So when what is Drinfeld space at infinite level? So it's related to this Drinfeld upper half space. Namely, by definition, the Drinfeld tower is a tower of finite étale coverings of the space omega 2. And so, in particular, there's somehow a tautological map down to omega 2. And this projection is a pro-finite étale map in a suitable sense. And so this composition here is the Scholze-Tate period map. You all squash them down, so we forget about this.
This finite set is parameterized by, so to say, super singular elliptic curve.
Yes, yes.
Gamma level.
Yes. What to say? So in particular, on this part, the fibers of the Scholze-Tate period map are some pro-finite sets, whereas on this part, they are some one-dimensional guys. So the dimension jumps. Okay. Okay. So that's supposed to give some impression of what this map looks like. And so I wanted to give a slightly different perspective on what this period map actually does. And for this, I need to state a theorem in my joint work with Gerard Weinstein, which says the following. And so I said yesterday that it's useful to look at other algebraically closed and complete extensions of QP. And in this theorem, it's actually quite important. So let me explicitly do this here. So you might take C equal to CP. Then you can classify p-divisible groups over its ring of integers by the following data. There is lambda and W, where lambda is just a finite free ZP module. And W is just a subvector space of the scalar extension to C. And the map, the functor, is given by taking such a p-divisible group and mapping it to its periodic Tate module, which is equipped with its Scholze-Tate filtration. So yesterday I was talking about the Scholze-Tate filtration for the BM varieties, but in fact there is also a Scholze-Tate filtration for p-divisible groups, which is compatible with this picture. So that's some kind of analog of the classification of complex tori So complex tori are also classified by their first singular homology group, which is some finite free Z module, together with a Hodge filtration. Note also that this is a classification of p-divisible groups in terms of linear algebra objects. So usually you classify p-divisible groups in terms of semi-linear algebra, like Dieudonné modules. But this is somehow a totally different kind of classification of p-divisible groups. So what does this mean? So this theorem means that remembering the Hodge-Tate filtration is equivalent to remembering the p-divisible group. So at least if you work over geometric points. And in a situation where this guy has good reduction. So at least on geometric points of the locus of good reduction, you can consider pi Hodge-Tate as a map which stands in a BM variety A plus a mixture structure to its p-divisible group plus all the extra structure it has. And so in some sense, this flag variety is some moduli space of p-divisible groups. But, I mean, it's really only true on geometric points. So if you try to do this over a more general base, then the theorem fails. So, and also, if you try to make sense of some moduli space of p-divisible groups, you will see rather soon that this is a very, very ill-behaved object. So it is a stack, of course, but it's not finitely presented in any sense because a p-divisible group is a sequence of finite flat group schemes, and you have to give infinitely many. So the moduli space of p-divisible groups in itself is not so well behaved, but this flag variety gives you a well-behaved replacement for it. And so in fact, when I was thinking about local Lagrangians, I always wanted to project my Shimura variety to a moduli space of p-divisible groups. And I could never really make sense of this. And it was in this context that I first found this Hodge-Tate period map. Let me also now explain the role of this general C. So one proves the theorem first if the norm map on C to the positive real numbers is surjective and C is spherically complete. So such fields exist, but you can even sometimes explicitly write them down, but they are really, really huge, and they are much larger than CP. So, and CP fails both of these properties. So for the first proof, it's there, and then one descends in a non-obvious way. And maybe I should also say that for the experts, the theorem implies the description of the image of the Rappaport-Singh period morphism. Okay. Okay, and so now we can finally, honestly, start the proof of the lifting theorem. Okay. So we are interested in this compactly supported cohomology group. A priori of this complex manifold, but somewhat equivalently by some standard comparison results. You can also take this guy, this p-adic guy, and say this analytic space. Look at its complex supported Ital cohomology, which will be the same as. So that's we're interested in this. And eventually we want to go to some cusp forms, to some coherent cohomology. And so we want some comparison now between Ital cohomology and coherent cohomology. And in general, that's some of the business of p-adic Koch theory to relate Ital cohomology and de Rham cohomology also. But p-adic Koch theory, I mean, if you want something which works with FP coefficients, so we need some integral p-adic Koch theory. But if you look into integral p-adic Koch theory, then you will see that the usual statements only work if your variety has some kind of good or semi-stable reduction. But I want to let the level at p go to infinity, which means that this requires really, really bad singularities, mod p. And so these usual statements in integral p-adic Koch theory are of no use. And so instead one uses the following rather strange result. That if you, well, I guess my C is now CP. But you could take any C. So you extend scalars to the ring of integers of C mod P. And then there's a map I guess my notation is not the best. Well, I don't know. Okay. No. That's finite level. It's some kind of rigid analytic variety. This is still some kind of more or less classical stuff. And so there's a theorem that there is. So just by including OC mod P into this sheaf, which I will explain in a second, you get an almost isomorphism. So that's a statement that's proved in my p-adic Koch theory paper, but that's mirrored after a result of faultings. Okay, so what's the notation here? So first of all, I should explain the sheaf I plus. So that's the intersection of I and O plus in the structure sheaf O, where I is a sheaf of cusp forms. So all those functions which vanish at the boundary. And O plus is a sheaf of functions bounded by 1. Absolute value of that is just 1. The p-adic absolute value. And so what does almost mean? So that refers to faultings' so-called almost mathematics. Which is worked out in great detail in a book of Gaber and Romero. but what I need here is very simple. So a module as NOC module M is almost 0. If p to the epsilon times m is equal to 0 for all in positive epsilon. So in other words, it's very, very small torsion. It's killed by any positive power of p. Not just by p itself, but also by some all roots of p. And the map f from m to n is an almost isomorphism. If both the kernel of f and the co-kernel of f are almost 0. And because I asked it this very small torsion, that's really a statement which is non-vacuous when you work with FP coefficients, or rather when you work with OC mod P coefficients. Okay. So what do we have achieved here? So what we have achieved is that we have reinterpreted this cohomology group we're interested in as a cohomology group where at least some kind of sheaf of cusp forms appears. And of course, we want to get to cusp forms eventually. The biggest problem we have is that this is still computed, and that's crucial, on the étale side. So this whole mystery of the étale side is still there. And it's still very hard to compute what this is because you have to refine, you have to take some étale hypercovers or whatever. I mean, it's nothing you can really compute. So the problem is we need to take étale cohomology. No, I mean in the étale side of the rigid analytics variety. So you're essentially allowed to do things. You're allowed to pass to rigid analytic open subsets, and you're allowed to take finite étale covers, and everything you get by composition. No, and it's also really important to work with some kind of p-adic analytic spaces here. Because otherwise this sheaf O plus doesn't make any sense. So on some algebraic varieties, there are no functions which are bounded by 1, by some kind of p-adic version of Liouville's theorem that bounded holomorphic functions are constant. So you really have to work on p-adic analytic spaces. Okay. So comes step 2, pass to infinite level. Well, that's actually completely formal. And at this moment, it's probably totally unclear what this should be good for. So if I take the direct limit over all n of these cohomology groups at level p to the n, p coefficients, and then again tender this OC mod p, and then the result will be almost isomorphic to now the étale cohomology of now my infinite level Siegel space with coefficients in this same kind of sheaf I plus mod p. By the way, maybe I should say that taking complexly supported cohomology here manifests itself in the fact that I take here cusp forms, some of this usual dictionary. If I would consider the usual cohomology of the compactification, I would just consider O plus mod p here and so on. Okay, so what do we get here? So I should say that some of this left-hand side here is what's called completed cohomology mod P, maybe. So Emerton has this theory of completed cohomology where you pass to infinite level at P and then do the same thing for z mod P to the n for all n and take an inverse limit. And yeah, we are also passing to infinite level here. And so we are somehow reduced to understanding this group here. So the Tal cohomology on my infinite level Shimura variety with coefficients in this sheaf I plus mod P. Okay. So now we actually use that this guy is a perfectoid space. So this has a consequence. And I can't really explain why this is true, but it's somehow really relying on this property. If I have an affinoid subset of this guy, then I can actually compute the Tal cohomology on U of the sheaf I plus mod P. And it's as simple as it could possibly be. Namely, up to some very small torsion, so almost, it's just cusp forms on U mod P, phi 0, and 0 in positive degrees. And nothing similar would be true at finite level. Yes?
Isomorphism is again like a Hodge decomposition or what is it? That almost isomorphism which you say?
Yes?
Is it again like some kind of Hodge decomposition?
Yeah, it's some kind of periodic Hodge theory isomorphism. But some of our torsion coefficients, which is crucial. And yes, it is some of the key ingredient in proving, say, this Hodge spectral sequence and so on. It is some of the key comparison which allows you to go from a Tal cohomology to coherent, to any kind of coherent cohomology. It's a general statement, yes, about proper rigid analytic varieties. So it doesn't use it as a Shimura variety or anything.
Customs and some weights and so on, I think maybe, and
No, I mean, just somehow with trivial coefficients, right? I mean, just inside the structure sheaf. So there are, of course, no global sections of this sheaf. But, okay. And so this means that we can compute this Tal cohomology group we're interested in. Via a Čech complex whose terms of the form I plus on U mod P for some kind for varying affine U inside of this guy. And now we're already in a much better position because now we've eventually related our Hecker eigenvalues appear in one of these groups here in the beginning, then eventually we can show that they will appear in this group by this comparison isomorphisms, and then they have to appear inside this group for some U. So this means that at least on this affine rate subset, we can find a cusp form with the correct Hecker eigenvalues. But we want a globally defined cusp form. So by a cusp form on U.
So do you use the period map here to get this good use or
Hmm?
do you use the half state period map?
Not yet. It enters in a second. Okay. Do we have any space here? Not so much. Okay, so now we've realized our Hecker eigenvalues, at least by some cusp form on some affine rate subset, and we just need to approximate this now by a globally defined cusp form. But of course, without messing up the Hecker eigenvalues. Without. I mean, so in some kind of Hecker equivariant way. So in particular, we want an eigenform. So how does this work usually? So in some sense, this is a classical situation which goes back to maybe Katz's paper on periodic modular forms. So what he does there is he considers these periodic modular forms which he defines as being defined on the ordinary locus, but having some arbitrary poles away from the ordinary locus. But then he approximates them by classical guys by multiplying by a large enough power of the Hasse invariant. So the Hasse invariant vanishes at all the supersingular points. You can remove all the poles at the supersingular points if you multiply by a large enough power. But on the other hand, the Hasse invariant commutes with all the Hecker operators away from P. And so it doesn't mess up the Hecker eigenvalues. So usually you would be in a situation, so usually in this business of periodic automorphic forms, you would be in a situation where U is the ordinary locus. And what you do is you multiply by a large power of the Hasse invariant. And so the two properties of the Hasse invariant you need is that this vanishes outside U, outside the ordinary locus. And secondly, that it commutes with the Hecker operators away from P. So often one says that one uses that the Q expansion of the S invariant is just 1, but a much better way of saying it is that really it commutes with the operators away from P. Okay, and so you need to, but, okay. So we can't ensure that you use the ordinary locus because we're really building this Czech complex by covering our whole space by these affine subsets. So we need something which works on any part of the Schmidl variety. Yeah, but we need functions that commute with the operators away from P. But now the state period map enters, namely any function or better section of an automorphic vector bundle. That comes via pullback along the state period map from the fact variety will commute with the operators away from P. Because the hot state period map had all these properties. And so this gives us many candidates of, well, I guess in my paper I call them something like fake Hasse invariants. To work with. And in fact, there are enough of them, namely, because this hot state period map is affine. There are enough of those. To make the argument work. So what you do is you pick an affine cover of the flag variety and you pull this back along the hot state period map. Because it's affine, this will give you an affine cover of the infinite level Schmidl variety, and you use this affine cover to build this Czech complex. And then with that affine cover, you will be able to get the arguments through. Okay, now I have a couple of minutes left, so I can take suggestions of what to explain in more detail. For example, I might give some indication of why this guy is perfectoid and what this means. Why? So let's do this just for the modular curve. Okay, so first of all, very brief definition of perfectoid algebras. So there are some kind of Banach algebra, so a Banach, say CP algebra, R is perfectoid. If two conditions are satisfied. The first is a somewhat mild topological condition, which is a slight strangling of being reduced. So it says that if I look at R0 and R is a subring of power-bounded elements, that this guy is a bounded subring. So a different way of saying this is that the spectral that R is complete for its spectral semi-norm. So in particular, the spectral semi-norm is a norm and it's complete for that. And something you can always replace a Banach algebra by one for which this is satisfied by just completing for the spectral semi-norm. So that's some kind of mild condition. So the crucial condition is that the Frobenius. So this is some kind of integral subalgebra in R. So now I can mod out P, get something non-trivial, and there I can look at the Frobenius map, which sends x to x to the P. This is supposed to be surjective. So the standard example of such a guy is something already very big. So you take some kind of Tate algebra, not just in a variable t, but you also join all p power roots of t in there. Okay. So those are some algebras where there are lots of p power roots, or at least approximate p power roots. So the surjectivity means that you can always write an element, an integral element, as p's power at least mod p.
So what does this bracket mean?
Tate algebra. So to be completely precise, you take the usual polynomial algebra, C, with t and all its p powers adjoined, so meaning the direct limit of the algebras where you join a p to the nth root. And then you complete this p-edically, and then you invert p again. T is a formal variable, yes. So these have all sorts of funny properties. So for example, the category of such perfected algebras is equivalent to a category of perfect characteristic P algebras. So this category of characteristic zero algebras is equivalent, literally equivalent to a category of characteristic P algebras. But, okay. Those are these perfected algebras. And I want to give some indication why this modular curve should behave in this way if you go to infinite level. And so for this, you look at the modular curve at level 0. So full level, say. And let's look at this mod P. And so mod P, it's just a smooth curve, and it has a bunch of supersingular points. Which don't look very special for now. But then we can increase the level at P. And so, for example, we can look at gamma naught P level, mod P. And then Deline and Rappaport give a description of what this looks like. And so it has two irreducible components. And they meet in the supersingular points. Two irreducible components. And of those two irreducible components, there's one which maps down via an isomorphism. And the other one maps down via Frobenius. Okay. And so if I go to even larger level, not p to the n, then this has n plus 1 components. So let me call this one which maps down via Frobenius. Let me call this the anti-canonical component. Because so this parameterizes subgroups of the p-torsion of the elliptic curve of order p. And on the ordinary locus, there's a canonical one. And this component where it maps down isomorphically is the one where you choose this canonical subgroup. Whereas on this other component, what you do is you take an orthogonal complement to this canonical subgroup. Okay, so on this guy, mod p, there are n plus 1 irreducible components, which all meet again at the supersingular points. Precisely one maps to the anticanonical part. Anticanonical component. And it does so via Frobenius. So this means that if I look at this tower of modular curves of increasing gamma naught level, just above this anticanonical component, then the transition maps will just always be Frobenius mod p. And so this means that if I pass to infinite level, then this will somehow become perfect mod p, and this also implies this perfectoid condition somewhere on characteristic 0. So above the anticanonical ordinary locus. And how to continue my discussion? Okay, so we have at least, okay. But that's just for gamma naught level, and we really want to go to full level, so gamma p infinity. But in fact, the almost purity theorem, which I didn't state, but a weak form of it says that if R is perfectoid, and S over R is finite étale, then also S is perfectoid. So this property is preserved under finite étale covers in characteristic 0. And because going to a higher level in characteristic 0 is the finite étale covering map, this implies that also at full level at infinity, this property remains true. That's a priori not so clear. Yeah. And so there is one component at least, so some of the totally canonical component, which will not become perfectoid at this level. Okay. Let me briefly finish this discussion by explaining how one goes to the full modular curve. Namely, one uses a theory of the overconvergence of the canonical subgroup. to show that in fact all the same is true in a strict neighborhood of this locus. Also is anti-canonical. So we are just slightly entering the supersingular disks. But this turns out to be enough. Namely, so you have GL2QP acting on this modular curve at infinite level. Maybe just as a topological space or so. And at the locus where it's perfectoid, is stable under this action. And so you can try to move around the strict neighborhood of the ordinary locus under this group action. And then what you see is actually that then it covers the whole space. So this is more or less equivalent to saying that if you have an arbitrary supersingular curve, then you can always find an isogynous one, which is as close to the ordinary locus as you wish. I don't think this was known before, but you can deduce it somehow from the Odd-state period map in some way. But anyway. So both of these are some kind of infinitized rigid analytic spaces. And it's extremely hard to make precise what they are. And so both Faltix and Farr, when they formalized this, they were working with specific formal models for these guys. So of course it makes sense to talk about formal models of infinite time. But these formal models, they're not very canonical, and so they have to work really hard to get them. But now the theory of perfectoid spaces, first of all, allows you to give them these spaces a canonical structure. So both of them are perfectoid spaces. And in my paper with Jared Weinstein, we give a modular interpretation of these infinite depth spaces, which is in some sense independent of p-divisible groups, just in terms of p-divisible theory. And once you have that, the verification of isomorphism is just some basic linear algebra.
You know, there was this conjecture of Langlands about points mod P of similar variety in terms of group theoretic data,
Yes.
which was proved by corporates.
Yes.
So I wonder whether these perfectoid spaces also have somehow group theoretic way of interpreting their points.
Well, there are so many.
There are
so many. And somehow points over finite fields, they are only finitely many or so. You can try to parameterize them.
I mean, I think the conjecture of Langlands was the points over FP bar together.
Okay, FP bar is still modules. Yeah, and I wouldn't think so, but I mean, he's really crucially using that in FP bar points has complex multiplication and so on. And so somehow nothing similar is true somehow for a generic point, or for a characteristic 0 point.